This week, we're going to cover numerical solutions to ordinary differential equations. This topic is covered in Greenberg, Chapter 6. What I'll talk about in this video is first an introduction to methods of quantitative analysis, numerical methods being a very powerful and commonly used uh, example. And then I'll go over a very simple numerical method using Euler's equation. After showing you how to what Euler's equation is, I'll discuss the accuracy of Euler's equation and how to assess it. After viewing this video and working through the problems, you'll be able to write a computer program that solves a first order ODE using Euler's methods, and you'll be able to explain how the accuracy depends on the step size by which you discretize a solution using numerical methods. So again, I'd like to encourage you to write out that objective. And I won't write it out for you now, but please start your notes by writing out that objective and keep that in mind as you work through this video. Okay, so an introduction to numerical methods is the first topic. Now, so far, we've learned different ways of producing analytical solutions to an ODE. And for example, the first order ODE was y prime is equal to some function of x and y. And these solutions, they can be written in closed form. Just introducing you to some terminology. That is, you can write them on using a pen and paper completely as y is equal to the solution. This is the big S representing a function being the solution, and you can write it out completely, and the solution is exact. So we've learned how to produce exact closed form analytical solutions of the equation of this form. And that of course is the best way to solve a differential equation. However, many differential equations, actually the ones that apply to real systems, are too complicated to solve analytically. Therefore, we must rely on different methods to solve them. So in the case of numerical methods, numerical methods produce approximate solutions at discrete points. And those approximate solutions are often very accurate. but again at discrete points. These are discrete points in space or in time, depending on the problem. So numerical methods are extremely powerful ways in which scientists and engineers solve complex problems. For example, if you're designing an airplane, you would use a numerical analysis or numerical methods to predict, for example, the stress or fatigue on your airplane wing. Scientists use numerical methods to study or simulate ocean circulation, tsunami wave propagation, and how it affects coastlines. Climate and weather modeling is done numerically, and many problems in earth science, solid earth science, such as earthquake predictions, um, magmatic processes, are addressed using numerical models. Now, one of the main drawbacks of numerical models is you cannot see how the answer depends on a particular variable in your equation. For example, when we looked at the mass on our spring, we saw the solution in terms of the mass of the object, um, the constant on the spring, as well as the coefficient of friction that described the viscous drag of the object on the surface of our between the mass and the surface on which it was sliding. But in numerical methods, the direct relationships cannot be seen. So it's very important. It's just as important to produce the solution as it is to understand those relationships. So numerical methods require quite a bit of analyses to understand the relationships between those input parameters and the solutions. So that's just some overall insight on numerical methods, and you'll appreciate those aspects if you start using them and applying them to a particular problem. But now let's get into sort of the practical aspects of the class, and that's looking at solving a numerical problem, an ODE, using Euler's method. And again, the problem at hand is solving the slope of y prime, as a function of x, being described as a general function. So again, this is the slope of y as a function of x. And so that's the problem. Oh, and we may have an initial condition that y at point A is equal to b. This is our initial condition. So I'm going to sketch out an example that Greenberg shows in a figure. So we have x and y, and we are given the solution of the slope. And so if we know we're given the slope and we're asked to solve what y is at various points in space. So here I'm sort of drawing little tick marks representing the slope at various locations. And I'm showing the slope increasing as you increase in both y and x, for example. So this again is the slope f as a function of x and y. And the idea behind Euler's method is to start at our starting point. X sub 0 is again equal to point A. This is our this is our starting point, which for which our initial condition is defined. And that initial condition, for example, is y is equal to b. So y0 is equal to b. So our starting point is right here. And to illustrate Euler's method, what we're going to do is we're going to estimate the value at y. And again, the estimate can be quite accurate depending on our method. and we're going to estimate it at various points, x1, x2, x3, for example. And this is by dividing our space into discrete points, we're discretizing our system. And here the spacing between these different points is what we'll refer to as h. That's the spacing by which we discretize our model space. And so to outline the method, we're going to start off at our initial condition, and we know what the slope is at this point. So we're going to project our solution along that slope to our next point in space, x1. Okay, so this is our estimate for y1. And then starting from y1, since we have an estimate for y1, we know where we are in xy space, so we'll project along the slope evaluated at that point, which might look something like this. And we'll project that to point x2. And since we know we have an estimate for our new position at x2, we can evaluate what the slope is using our function, and we can then project along that slope to our new point, x3. And y3. So this is x2, y2. This was x1, y1, and so forth. So you can see, so this is a summary of the strategy. Now let's show how we're going to go about doing it. So again, the first step was to start at our initial condition, that is y of a is equal to b, and that is x0 is equal to a, and y0 is equal to b. This is our starting point. And then we're going to project along a line of slope f evaluated at point A and evaluated at point B. And we're going to project across a distance in x of, say, delta x is equal to h. And this gives us y1 at point x1. So projecting along that first slope gives us this first point. And then the second step is to start at x1, y1, project along the slope f evaluated at x1, y1, a distance h, to get y2 at point x2. And then we repeat the solution, or repeat the procedure for subsequent values of x's and y's. So it's a pretty simple method, and conceptually it's quite simple, and it's also relatively simple to write out. And so we can write out the solution at point n plus 1 as being equal to the solution at point n plus, when we project along the slope, our slope is f evaluated at xn, yn, and the projection is over a distance h. So this is our run, this is our rise over run, and so this gives the net change in y from point n. And so so Euler's method is written out like this, and we're going to do this for n equals 1, 2, 3, starting at point A and B. Actually, to be consistent with my initial notation, we would start at n equals 0. So n would go from 0 to 1, 2, and 3, etc. So let's show how we would write that out in a MATLAB type code. So, for example, we would define h. Say we would do that by saying h is equal to some number. And we would define the vector x is equal to, say, a, which it was already defined, in increments of h to our maximum, the maximum point at which we want the solution, x max. So of course these need to be defined. A and x max need to be defined. And I like to make this a column vector by putting a prime there, and then we put our semicolon. So when we run it, we don't see the whole vector display on the screen. And so we might create a variable called nmax is equal to the total number of elements in our vector, and that would be length x. And then we could write a for loop in which n is a variable that varies from 0 to n max minus 1. So this is going to vary n from 0 in increments of 1 up to n max minus 1. And we would say, for example, that y of at point n plus 1, the n plus 1 value of vector y is equal to y, the nth value of y, plus whatever our function of the slope is, times our step size. Okay, so for example, Greenberg shows a case in which the problem at hand is y prime is equal to y plus 2x minus x squared. And with that example, we would write y of n plus 1 is equal to y at point n plus, now the slope is y at point n plus 2 times, and you need the dot star to multiply each value in vector x by 2 minus x and then a dot caret to raise it to the second power, to raise each number in x to the second power. So again, this is the slope given by this function. Oh, and of course I have to multiply it by our step size. And then we end it. And so this would produce solutions at each of the points all the way up to this point x max. And that's a simple This is basically the essence of a code that applies Euler's method. So I think I'll end this video here and talk about errors in the next one. So again, we had an introduction to numerical methods, and we talked about how to how to use Euler's equation for a very simple way to numerically approximate the solution for a first order ODE.